The first and foremost measurement we get to know in our life is the weight of our body. So we have a little idea about the weight since even our child age. We are going to describe in this video what the weight is, how we feel it, and whether you can find the same number for your weight at wherever in the world. If you watch this video until the end, you can have a very good piece of knowledge about weight. Come and enjoy Art Science, which touches the artistic places of science, and makes people informed. Then let's discuss the aforesaid facts one by one. Number 1. What is the weight? According to Sir Isaac Newton, there is an attraction between every couple of masses in the universe. That force is given by the formula, F equals G times m1 by m2 over r squared. Here m1 and m2 are the particular couple of masses, and r is the shortest distance between those masses. G is the universal gravitational constant. So according to this, the Earth exerts an attractional force on our body. Why? The Earth is a mass and our body is also another mass. This force is called our weight. Now do you think we really feel, or experience this attractional force as weight? You might be thinking so. But the reality is another thing. Then let's inquire what it is. If the only force exerted by the Earth on you is this attraction, you must be pulled towards the center of the Earth. Cause according to this imagination there's no force to balance the weight. As Newton's first law says, until an imbalanced force exists on an object, it's accelerated. This can also be described using F equals ma when F is non-zero. Is also must be non-zero, cause m is the mass of the object and it can never be null. But the reaction made by the Earth's surface occurs on the body and prevents that pull. Do think very well. Guide your mind to the reaction on your body at this moment. It could be exerted upwards on you occasionally, by the ground if you're having stood up, or by a chair if you're having sat down, or by water if you're swimming. If you're now still relative to the Earth, the only force you can sense now is that reaction, not the weight. So you recognize that you have a weight because of that reaction made to balance the weight. Then I'm gonna prove this idea. Let's look how. Someone who jumps from a high place or an astronaut does not feel this reaction. So he doesn't recognize that he has a weight. Hence he senses a zero gravity situation. What do you think is the reason for this incident? When someone jumps down, according to F equals ma, an acceleration is made on himself by his weight. So no reaction is needed for the equilibrium. An astronaut is always on a fixed orbit, revolving around the Earth. When an object is engaging in a circular motion, it always experiences a pull towards the center. This is called centrifugal force. Let me describe this to some another little extent. This object is engaging in a circular motion on a horizontal plane. Now consider this position. Forget the vertical forces for a while. If no horizontal force occurs on this, at the next moment, this would travel this side. Why? According to Newton's first law, it must be a linear motion if so. But this object has to turn this side here. For that, there must be a pull towards the center on it. This is the so-called centrifugal force. The attraction made by the Earth on the astronaut, absolutely his weight, acts as the centrifugal force, and so that there needn't to be any reaction to balance the weight. So he doesn't feel weight. As well, an astronaut could be in the space. The space is defined as where there's no non-zero resultant force on any object. All the forces on an object are balanced together. So he doesn't experience any reaction, and so that doesn't recognize he possesses a weight. Although we simply described the weight as the gravitational force exerted by the Earth, it is merely not so. Since the Earth rotates around its axis, we also revolve around its axis. The centrifugal force demanded by the circular motion is to be provided by the gravitational force. So the reaction equals to the difference between the gravitational force and the centrifugal force. This is the globe. It rotates around its axis with a constant angular velocity. The centrifugal force is given by the formula, Fc equals mr omega squared. Here m is the mass engaging in the circular motion, r is the perpendicular distance between the mass and the axis, and omega is the angular velocity, which is the angle rotated for a second. Wherever on the Earth, m and omega are constant. Only r differs. When the man stays close to the equator, r is bigger, and when he is close to the poles, r is smaller. The greater the r is, the greater the Fc. When r is the reaction, Fg is the gravitational force, and Fc is the centrifugal force, r equals Fg minus Fc. Because it costs some little part of the gravitational force on behalf of the centrifugal force. The greater the Fc is, the smaller the r. So close to the equator, r is smaller than close to the poles. So there's a little greatness of the weight when it is measured close to the poles, rather than when it is measured close to the equator.
Thank you for watching this video. If you gained something from this video, don't miss to like it and share it. Subscribe my YouTube channel for more video like this. Click the bell icon for getting a notification about my channel. See you again.